This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Alright, good morning everyone. So Dragon is away this week, so I will cover some, the rest of the tutorial problems and some of the exam questions in this week. So, the plan is I will quickly go through the leftover tutorials. So tutorial 7, 8, and 9. And then, tutorial 9 is mostly exam questions. So starting from there, I will start to talk about exam questions, like past exams. So if you want to prepare for this, I would recommend you to go through the 2018 and 2017 exam papers first, because that's the most recent ones. If we have time, we will try to cover something from 2016 and 2015 papers as well, all right? All of them are available on LMS, all right? So if you cannot find it, let me know. But it's under resources, all right? Okay. So firstly, this is tutorial 7. All right. So we're gonna start with the first question. So the first question asks, so this is the transfer function that is given, and it let us show that we can write this down. Any idea on how to do that? Well, first of all, can everyone hear me? Can everyone hear me? Okay, cool, thank you. So any idea on how to do this? Yes, so this is very straightforward. So you just substitute s equals to j omega n, and then you can write it as, it will be omega n squared over j omega n squared plus 2c omega n j omega n plus omega n squared. Right? And then you open up this, you know that j squared is equal to -1, right? So this is negative omega n squared plus 2c omega n squared j plus omega n squared, and you have omega n squared on top, right? And then you can see this and this cancels out, right? And what it leaves you will be, and after that you can cancel out this omega n squared as well, right? So after that you have 2zj with 1 on top, right? And then if you take the magnitude, it will be really straightforward. It will be just 1 on 2c. Is everyone following that? Okay, so that's question 1. So now we move on to question 2. So in question 2, it asks us to sketch the body plot by hand. Alright? So starting from A. So in A, we have GS equals to S plus 2. Right? So what's the first step? The first step is to write it in the form as this. Right? Is everyone following this? Okay. And then you can see that this is just a combination of two terms. The first one is just a constant 2, and the second one is this, right? Okay, so now we can draw the body diagram of this transfer function. So firstly, so what is a body plot of a constant on the game plot? It's just a straight line, right? So well, this is in decibels. This is that's the magnitude. This is the phase. All right. So you can calculate that 20 log base 10 2 is roughly 6.02, right? So you can find somewhere 6.02 and then draw a straight line, right? And how is that on a phase plot? How is a constant on a phase plot? 0, yes. For example, if this is 0, it's just along this line, right? Alright, so that's a constant 2. And now we're gonna draw this part. So first of all, we can see that the corner frequency is at 2. Right? Okay, so we find 2. And, well, we can write it in another form. We can write it as, right? Well, this is j omega. Right? We put j omega here, and then we can see how the magnitude and phase change with the change of omega, right? So when omega is far greater than 2, then what happens? So, sorry?
Phase is 9.
Sorry?
Phase is 9.
Oh, yeah, well, we concentrate on the magnitude first, on the gain first. Alright, so if omega is greater than 2, what happens here?
Increases between
Yeah.
Increases.
Yes, increases. So we know that it increases with a slope of 20 dB per decade, right? And when omega is far lower than 2, what happens? Yes, so this term will become really small, right? So it's, well, if this is 0, then it's just here, right? Alright, let's come to the phase. Yeah, so when it's really small, when it's far smaller than 2, so the phase will stay as what? 0, yes. And as someone just mentioned, when it's way greater than 2, it will jump to 90 degrees, right? So if you combine these two lines, you eventually have something like this, right? Sorry, this. Right? Oh, this should be 45 actually. In reality, it's smoother, so you get something like this. Alright, so that's for A. And actually you can check against your answer that it looks like this. Okay, let's move on to B. So in B, you have GS equals to 1 over S plus 5, right? So if you know how to draw this, it shouldn't be too hard for you to draw this. Why? Because this is just, well, you just change 2 to 5, and then instead of having this, now you have 1 minus this, right? And this looks something similar to what you've drawn before, right? So, we can split this into 3 parts. The first part is 1. The second part will be 5. The third one will be S on 5 plus 1, right? For the constants 1 and 5, it's quite straightforward, right? So again, you know, the constant 1 is just say if you have 0 here, I should draw it longer. The constant 1 just gives you a line along 0, right, on the magnitude plot, right? This is face. 5, because it's on the denominator, so we need to subtract that. So if you take 20 log base 10, 5, it is roughly 13.98, right? So because that's on the denominator, you are subtracting that. So, so here it's up to you to how you draw it. You can draw every component on the plot first, and then you determine which one you need to subtract, which one you need to add, right? So I'm gonna stick with that, so I'm not subtracting now. So a constant 5 just looks like this, right? And for both of them, the face, you know that it's, well, let's draw it here. It's like this, right? And now this term, it's similar to what we've drawn before, right? So you find 5. On the magnitude plot, you just have something like this. It's a slope of 20 dB per decade, right? And on the phase plot, you have, say this is 90. You have something like, oops, this, right? And now you combine them together, right? So this is a term on your numerator. Both of them are on your denominators, right? So now you take this and subtract this and this. So, well, this is for 1, this is for 5, this is for S on 5 plus 1. This is for S on 5 plus 1, this is for 1 and 5, right? So now you combine them together. So you get, this is negative 13.98. Now this, you have, this is negative 19 degrees. Right? There's no peak here, this is straight. And in reality, you get something like this. Sorry for that. So this is the plot for 1 on S plus 5, right? And once you have both of this, it's really simple to get the rest of the plots, right? So here, C is just a combination of these two, right? So you take out your plots, this one and that one, you add them together, and suddenly you get C, right? For D, it's just on top of C, you add another B, right? And for E, well, for E, you have a pole at origin. So how does that look like? So what's the body plot of 1 on S? What is the body plot of 1 on S? Again, this is magnitude, this is phase. Yes, I saw that. Yes, it's a straight line with a slope of negative 20 dB per decade, right? And something more importantly, where do you cross the x-axis, the horizontal axis, the frequency? 1, right? Can everyone see this? So you can write it in the form of j omega equals to j omega so on top, right? And then you can see that at omega equals to 1, you have that crossing, well, sorry, this should be 0 dB, right? And how about the phase? So what is the phase plot of 1 on S? So I'll give you a trick when you're plotting body plots. So what you can do is that you can look at the complex plane. So this is the real axis, this is the imaginary axis, right? So 1 on S is just you plot 1 and then you subtract S, right? So how does S looks like? So S is just j omega, right? So j omega means you don't have any real part, right? So which means you are traveling along the imaginary axis, right? And well, we are talking about j omega here. So as omega increases, you are traveling up along the imaginary axis, right? And as you travel, your phase is always 90 degrees, right? And here, since it is 1 on S, So you need to subtract that, so you have negative 90 degrees, right? So if this is 0 degrees, this is negative 90 degrees. This is how your phase plot looks like. Right? Okay, so now you have this. You have this part from D, you just add them together, and then you get your E, right? And similarly, you just add this term to E, then you get F, right? Okay, so that's question 2. If you're not sure about this, you can go back to the lecture recording and listen again, or you can use MATLAB to plot them out and see how that performs, right? Okay, let's move on to question 3. So question 3 is saying you have a open loop frequency response which is plotted like this, and it asks you to firstly identify the transfer function, right? And then based on the transfer function, you can then sketch a step response. Alright, so you've just plotted several body plots just now, right? You have all these plots, right? So what kind of combination can make this kind of plot? Well, firstly I need to say this, the unit of this axis is not decimal, right? This is just magnitude, right? Okay. So which combination can give you something like this? Any idea? Did you say S on S plus 10? S on 10 plus 1? S on 10 plus 1? Alright, so firstly, here. So this is a 0, right? The plot looks like this. So it's, well, this is the magnitude plot, right? So we focus on this one. So it starts from something horizontal and then increase. This is a pole. It starts from something holds as a constant and then decrease, right? And here comes a pole at origin, right? And it acts like a decreasing line throughout all the frequencies, right? So here, if you're on this decreasing trend at the beginning, you have to get a pole which is at origin, right? So which means you know that you have 1 on S in your transfer function, right? Okay, so if you get 1 on S, your plot actually looks like, well, this is frequency 1, right? So we'll replicate that. Your plot actually looks like this, right? So what is missing from this one to that one? You need something to lift it up. Sorry, this is at 1 as well. So if you convert 1 to decimal, it will be 0, right? So from here to here, you're still missing. Firstly, you need some constant to lift it up to 10, right? And secondly, you need something to bring this bit up to 1, right? So basically you need this and that, right? So you know you have a 1 on S, which is this line. What else is requested is this, a constant, and something like this, right? What is this constant? 10, because it's crossing 10 here, right? And what is this? Oh, sorry, my mistake. It is rising here. What is this? It's not S plus 10, because in the low frequency it's at 1. So it's S over 10 plus 1, right? And now we can put all of them together. Well, this is 1 on S. So you put all of them together, you have 1 on S times 10 times S on 10 plus 1, right? Now you get that's S plus 10 over S, right? But something you need to be really careful about is that because in this question it just showed a magnitude plot, it didn't show the phase plot, right? So you actually don't know whether there's any negative sign inside your transfer function, right? So which means actually you have a lot of possibilities, but that really depends on your phase plot, right? But this is one of the candidates. Okay. So now we have the transfer function, say, well, now we have the transfer function as S plus 10 over S. And now we need to sketch the step response. How do you do that? Sorry? Oh. So with 1 on S, you're crossing the magnitude axis on 1, right? But here it is crossing at 10, right? So you need something to lift it up, and as it is crossing the line at 10, so you know the magnitude is 10. What are you saying? This line?
Yeah. Why can't it be 1 over S plus
1 over S plus 1. Are you suggesting that's a possible answer, or are you asking?
Yeah.
So if you are talking about 1 over S plus 1, so in that case, you can split it in two parts. One is the constant 1. the other is s plus 1, right? And then you can draw the constant 1 just as 1, right? And s of s plus 1, again, it looks like this, right? This is 1. And you use this to subtract that. Eventually you get something like this, right? But that doesn't look like that. So this case, it's similar to this, right? You just change 5 to 1. Alright, so coming back to this. So now you have the transfer function. How can you sketch the step response? So a step response is represented in time domain, right? So the first step is that you take inverse Laplace transform, right? So you have your GS equals to this, and then you take inverse Laplace transform of your GS, and that will give you, well, you do partial fraction expansion first. This equals to 1 plus 10 on s, right? So you do inverse Laplace transform. The 1 is just a unit step, right? Oh, sorry, my bad. It's a unit step response. So you have your output equals to the input times your plan, right? So this gives you, right? Now you do partial fraction expansion. You get right? Now you can do inverse Laplace transform to your output, and that gives you, this is just a unit step. This is 10 times t, right? So it's 1 plus 10t, right? And now you can sketch it. So this is just a straight line, right? And the slope is really just 10. Right. Okay, so that is your tutorial 7. Okay, now let's move on to tutorial 8. Right. So tutorial 8 focus on Nyquist, right? So first question, it is asking, so there's a system G that has 2 unstable open loop poles, and this is the Nyquist plot, right? So first of all, let's revisit the Nyquist stability criterion. So it is derived from the Cauchy principle. So it is looking at the number of unstable open loop poles and the number of encirclements you are making to the critical point, right? And with these two information, you can then get how many unstable closed loop poles you have in your system, right? So you have that formula, which is already here, N equals to Z minus P, right? And you can reorganize it as Z equals to N plus P, right? So what does that mean? So N is the number of clockwise encirclements with the critical point, right? P is the number of unstable open loop poles, right? And with these two information, you can then calculate how many unstable closed loop poles you have, right? And that will tell you your stability of the system, right? Okay, so with that bear in mind, we can come to this question. So it's saying GS has two unstable open loop poles, right? So now we know P equals to 2, right? And the Nyquist plot is given here. How many encirclements do we have? 0, right? So our N is 0, right? Using this formula, we can then calculate Z equals to 0 plus 2, which is 2, right? What does that tell you? So that tells you you have two unstable closed loop poles, right? Which means your system is unstable. All right. Question 2. It is saying you have a plant like this, a controller like this, and a unity feedback loop, which is shown here. And it asks you to use the following methods and find the range of K for which the closed loop system is stable. So I've copied this to transfer function here, right? So this is the plant, this is your controller. Alright. Okay, so firstly, it asks you to use the Ross stability criterion to check your stability, right? So first of all, how is your, well, which polynomial should you check? Sorry?
Characteristic polynomial.
Yes, yes. So if you write down the closed loop transfer function, your closed loop transfer function actually looks like, right? And if you put them in and you reorganize the terms, well, I'll just write it. So it will be K times S plus 0.5, that will be S plus 2, S plus 0.5. Right? So if you multiply these terms on both of it, you get right? this is your characteristic polynomial, right? Because that captures the location of your poles for your closed loop system, right? So you can write it down. And you open it up. Then you can organize the terms. Right? And now you can write the table, right? So starting from s to the power of 3, s squared, s constant. And now you copy the coefficients down. 1, right? This is 2. This is k minus 1. This is half k minus 2. Right? So this term, using the formula, and then you get it is negative. On the denominator, you get this term, right? So it's 2 here. On the numerator, you get this times this minus this times this, right? So you have 0.5k minus 2, and this is minus 2 times k minus 1, right? This is this term. And you can simplify it as, well, that's right? And that gives you, that would be, well, you have negative, right? So you have a negative sign here, and then it comes to, right? Oh, sorry, this is 2. So you don't have this. Yes. Right? So this term is actually, right? Now you have this. Again, it is negative this on the denominator, and then you have this times this minus this times this on the numerator, right? But here, both of them are zeros, right? So you just get 0 here, right? And again, for this term, it's following a similar rule. It's negative this on denominator, and on numerator you have this times this minus this times this, and that will just give you this term. Right? So, to make sure that your system is stable, you will need the sign of the first column doesn't change, right? So to make it stable, you know your 1 and 2 are both positive, right? From here, you have right, and from this one, you have right. So this is the range of k that is required to make your system stable, right? So from here you get k greater than 0. From here you get have k greater than 2, so your k is larger than 4, right? So when you combine those, you get k greater than 4, right? That's the first one. That's a Ross criterion. So now we move to root locus. Alright, so you have a pole at, okay, so let's write down the poles. You have one at -2, right? For this, you have one at -1, another at 1, right? And the zeros, you just have one, -0.5, right? So you label them on your axis. You got a pole at 1. You got another pole at -1, -2, and a 0 at -0.5. Right? How does your root locus look like? So you know that if you have odd number of poles or zeros on your right hand side, that segment on the real axis belongs to root locus, right? So you know that this bit is part of your root locus, right? You also know that this bit is part of your root locus, right? And now you can calculate how many asymptotes you have, right? So you have 3 poles, 1 0, which means you have 2 asymptotes, right? And immediately you know that your phase is at, well, the angle is at -90 degrees and -270 degrees. Right? So if you follow the formula, the formula is giving you positive. So if you follow the formula, you have, I don't have the formula here, but the formula is available on your slides. So if you follow the formula, you get one as pi on 2, the other as 3 pi on 2, right? That's 90 degrees and 270 degrees. So you know that one asymptote is pointing upwards, the other is pointing downwards. And now you need to know where on the real axis does your asymptote intersects, right? So the intersection point, again, according to formula, it will be the sum of your poles minus the sum of your zeros. So it's like minus over the difference, like the relative order, actually. So it's 3 minus 1, right? And here you just get 1.5 over 2, which gives you 0.75. So you know that your asymptote is located here. Right? So now we know that your root locus is something like this. Right? Sorry? Which part are you talking about? Oh, like this? Because you need to, well, they need to meet each other first and then split up. So you can also calculate the I think it's called breakout point. If you are keen on finding this point, you can look up on Google. There are several examples teaching you how to do that. Alright? So, and now what you need to do is just to find the K at this point, right? So to find the K on this point, you can again use your characteristic polynomial. Where did I put it? Here, right? So your characteristic polynomial is s squared plus s cubed plus 2s squared plus k minus 1s plus 0.5k minus 2, right? Yes. You know that on this point, you have your pole located at 0, right? So what you can do is just sub in s equals 0, right? And then you get by solving this, you find k equals 4 at this point, right? So you know that as k increases, your pole moves from the open loop pole to your open loop zeros, right? So if you want it to be stable, it needs to cross the imaginary axis, right? Which means you need to have a k that is greater than 4, right? And lastly, by checking Nyquist stability criterion, the plot is given here. So looking at your open loop transfer function, you know that you have a open loop unstable open loop pole. So p equals to 1. So again, z equals to n plus p. In order to make it stable, you need z to be 0, right? Because that's the number of unstable closed loop poles you have, right? So to make it 0, you need n equal to -1, right? What does that mean? So it's -1, so that means you need to have a anti-clockwise encirclement, right? So your Nyquist plot is given here. It is traveling like this, right? So it is already counterclockwise. But here it's just -0.25. It hasn't encircled your critical point yet. So you know that by putting a gain here, you can scale up your Nyquist plot, right? So what you want is that you scale it until a point where you can have one counterclockwise encirclement with the critical point, right? So you know here you have, well, -0.25, which is -1/4, right? So what is a gain that allows you to make one counterclockwise encirclement? If you have a gain greater than 4, then you are sure that this point will pass through -1, right? So in that case, you have one counterclockwise encirclement, right? So if you check back the same system with Gauss criterion, you get k greater than 4. With root locus, you get k greater than 4. With Nyquist stability criterion, again you get k greater than 4, right? So with the same system, you know that you have different techniques to find the stability and also to find the range of K that allows your unstable system to stabilize, right? All right, I think we'll wrap up here. And from next lecture, we'll start from this question, which is a past exam question, and then we'll move to